After the last lecture, we're now ready to use what we've learned about line integration and heat and work in order to learn about something maybe more practical. And that's the answer to the question, how much heat is it going to take to raise the temperature of this system? So for instance, if I'm trying to boil some water and I'm going to do it by using a burner, I know that I'll need to add some energy in order to get the water from its temperature to the boiling point. How much energy will I need? Very practical question, comes up in all kinds of situations. Let's try to answer it using what we now know. So let's suppose that this is our state space M, and we're going to ask ourselves, if we want to follow this particular path in state space, which I'll call R, how much heat is it going to take to do that path, and what is the change in temperature? So if this is the initial temperature, and this is the final temperature, and this is the heat that we need to put into the path, what is the relationship between Q and delta T? More precisely, so question, what is Q? And in fact, let me call this Q sub R because this is the path R over delta T. Good. Now, immediately we see some sort of confusing or anomalous behavior here. The first is that this clearly depends on the path R itself. And so that might seem a little strange, but based on everything we now know about line integration and heat, it definitely needs to be there. The second is that it depends on how long this path is. And actually, we're going to get around that in a particular way. We're going to ask the maybe easier to answer question. Oops. What is the limit as, let's say, epsilon goes to 0 of Q sub R sub epsilon over delta T, where now we're going to say the path R sub epsilon only completes the first epsilon part of this path. And in the limit, this is going to tell us what is this change right at this initial point. Good. Now that we've defined the question, let's start to work with it. We know Q is by definition equal to the integral over R of T, and QR, is equal to the integral over R of T ds. All right. And immediately we sort of have a question. How are we going to evaluate this integral in general? Well, the answer is that we're going to need to choose a coordinate system correctly. And so let's be very cautious here. If we choose the wrong coordinate system, then this expression is going to become very complicated to work with. We're going to need to write out ds in these new coordinates involving all of the partials, and then all of those will be changing. We'll have to do a very complicated, ordinary line integral in the sense that you may have done in a calculus class. I want to make our lives easier using what we've already learned about differential geometry. We have the freedom to choose any possible coordinate system. So we're going to choose coordinates, t, and then a coordinate system a, I, such that AI is constant on R. All right, so this is very powerful. All of these AIs are going to be constant on this path, and that's going to help us out, as we'll see, enormously. Now let's re-express ds. So, as we've already learned, ds is going to be the partial of s with respect to t times dt plus the sum over I of the partial of s with respect to ai times dai. Now, I'm not going to specify this just for clarity, but when I say partial of s with respect to t here, I mean while fixing all of the ai. And similarly, when I say the partial of s with respect to ai here, I mean the partial of s with respect to ai while fixing all other aj for I equals not j, and also fixing t. Wonderful. Now we can say that qr is equal to, well, in this coordinate system, all of the ai are constant on r. And so in fact, the change in ai over this path is just going to be 0. In other words, that part should fall out. And you can look back through earlier stuff that we've done in order to see that that should be the case. So this just becomes t times the partial of s with respect to t dt. Good. Now we can finish this off by bringing ourselves back to this equation. So let's do that. We're going to take the limit as epsilon goes to 0 of the integral over r epsilon of t t of s dt divided by, well, we want delta t over this path. But there's actually a very easy way that we can express this using Stokes' theorem. We know that Stokes' theorem says that for a one form, the integral of that one form, the line integral of that one form over a path, is just the value of the function, and I need to back up. The line integral of an exact one form over a path is simply the value of the associated function at the endpoint of the path minus the function of at the beginning of the path. So what I should do here is put in dt. This line integral then will be t at the end point of r epsilon minus t at the beginning point of r epsilon, which is exactly the delta t that we wanted. Okay, we're almost done now. We have an integral expression in the numerator and an integral expression in the denominator. Let's think about what happens in this limit though. The length of this path is going to go to 0. So what will eventually happen, as you know from integration theory, if we integrate over an integral or an interval of length 0, we'll get 0. So both the numerator and denominator approach 0. But you'll know from an introductory calculus class that we have a way of dealing with that. We can just use L'Hopital's rule. L'Hopital's rule says that we need to take the derivative of the numerator and the derivative of the denominator. And the limit of this expression is exactly the same as the limit of the ratio of their derivatives if that limit exists. So we're in good shape here, because if I take the derivative of an integral, the fundamental theorem of calculus applies. And so what I eventually get is simply the ratio of the integrands after I do L'Hopital's rule. So if I say that this limit is equal to, and I'll say this somewhat suggestively, c sub r epsilon, by definition, then we are given that c of r epsilon is also equal to the limit as epsilon goes to 0 of t partial t s. And now let me restore that this depends on ai. Over, well, the integrand in the denominator is just 1. Now, also notice that this limit does not really depend on, what should I say, sorry, that in the limit, in fact, this just becomes the value of this numerator at the initial point here. So we can actually say in the end, CR sub epsilon is equal to t dt s, fixing all the ai, where this is now evaluated at the beginning of point of r epsilon. Okay. The only thing left to say about this is that this CR epsilon is called the heat capacity along this path. Or because now the path is limiting to a length of 0, it would also be reasonable to say that this is the heat capacity infinitesimally at that point in the direction of R epsilon. Good. We want to work out a couple of examples here. I'll make a supplement video in which I explain the relationship between the two examples that we're going to do. But the first one that I want to do is heat capacity at constant volume. So at constant volume, what do we get? Well, what we want to set AI equal to, and actually, let me be clear about something. We're going to do heat capacity at constant volume for a gas system for which the thermodynamic internal energy work coordinates are U, V, and N. Okay, so constant volume. That's going to mean that the AI that we need are N and V. We're going to fix the particle number through all of these. So if that's the case, then CV, as we often denote it, is equal to T dTs while fixing V and N. And this is a perfectly sensible expression if we work in the coordinates TVN. Good. Let's contrast that with what happens at constant pressure. In this case, CP is equal to, well, here we're going to have a little bit of an issue. And actually, I think maybe the easiest way to resolve that issue is to jump back up to approximately here. So let's jump up to our limiting case. So this is going to be QR epsilon over delta T. And what I'm going to do in this case is instead of plugging in TDS, I'm going to say that TDS is itself equal to du and then minus P dV. I'm sorry, sign error, plus P dV, where I've used the infinitesimal first law of thermodynamics to make that substitution. So what I get here is du on R epsilon minus R epsilon P, and again, sorry, P dV. And then that's going to be all over our delta T. Now, what are the coordinates that we should fix in this case? Here, we should work in a coordinate system in which we fix, or sorry, in which we use pressure, number, and temperature. In that TPN coordinate system, both P and N are fixed. So what do we get? For this first term, we're going to get delta U over this path. For the second term, P is a constant, and so it can come out of the integral. This integral of dV, well, that just gives us V, so that's going to be the change in V. And it's not too hard to see that what we get here is going to be the partial derivative with respect to t of u while fixing p and n plus p times the partial derivative with respect to t of v while fixing p and n. Now, this doesn't put us in a good position to contrast this example with our heat capacity at constant volume. So let's make a little substitution here. We know that we want to get U involved in here somehow. So let's, well, we don't really have very much space. But let's notice that I can say dTu, so partial T of U, fixing V and N, times partial U of S while fixing V and N. And replace that here for partial T of S. Now, this first term is, we don't have much that we can do with that. And I should say the first factor. This second factor, the partial of S with respect to U while fixing the other extensive coordinates, is precisely 1 over the temperature. So what happens? When we plug this in as 1 over T, that 1 over T cancels this. And so we get that the heat capacity at constant volume is simply the partial of U with respect to T while fixing V and N. Now we can more easily compare our two heat capacities. Here we have a partial of U with respect to T. And here we have a partial of U with respect to T. But notice that in these two partial derivatives, we've fixed different coordinates. Here we've fixed V and here we've fixed P. Fair enough. But in this case, we also get this second term. And this second term seems like it might contribute in some cases a lot since it's multiplied by P. In fact, we'll see in the supplement that CP is always larger than CV. In the next video, we're going to go over some example cases so that we can get a better handle on this before we move on. That's all for now. Thank you for watching.